Alrighty then. Well, the thing has been hit. It says we're live. Alrighty then. Hey guys, what's going on? Memes here. Before we get started, I want to wish a very swift recovery to a fractal faculty member of the Physics Monastery, Mr. Rick DeWitt. Swift recoveries, my friend. All right. But what are we talking about today? Today, well, we had said temperature, the Planck temperature. It's a limit of temperature. And also to finish our dimensions of reality, aka the five platonic dimensions of measure, I claim, is temperature. Because we've got length, we've got mass, we've got time, we've got charge, and now we need temperature. Now, of course, from time, length, and aka space, and mass. You can construct most things there. And since we know that mass and energy have equivalents, charge can be used to, I don't necessarily want to specifically say energy, but hey, I mean, we're running things right now on charge and everything. They're giving off temperature and everything. So basically, charge and temperature are also uh, forms of energy. We're going to say forms of energy because they take different forms and they coincidentally, by our reality, they seem to kind of balance out. Bada boom, bada bing, we're here as far as we know. Okay. So, as we've been listing down, basically, I'm stressing that if we have a coherent system of units, aka if you have something where F equals ma, that's just force equals your mass times an acceleration, and your energy is equal to that force times a distance, and then power, big P, is energy divided by time. Because well, if you unplug your computer and everything, assuming you have a battery backup there, you're going to be off that battery power pack, and it's going to estimate the amount of time you have because it's drawing that energy. See, look, real world examples and everything. But okay, we're talking about the Planck temperature, the limit of temperature. This is going to be very interesting because I might need to reframe this because technically, if we're going to put base units, the base actually is the Planck temperature. Ridiculously huge. See, this is why a lot of times people think Planck units. You're like, that's like really, really small stuff. It's like, okay, now for all these things that we have here, relative to our scale, we're on the meter-ish, about kilograms, maybe 100-ish kilograms, give or take. But generally about that magnitude is where we live. So most of these things are ridiculously small. The Planck length is okay, if we're on a meter-ish scale, yeah, it's about 35 magnitudes smaller. Now, the plankton, that's like for our one Mississippi, yeah, that's like 44. Basically, you need 44 zeros before that second before you're going to get around that magnitude. And then the Planck charge, it's really, really small. Okay. Now, the Planck mass, it is really small, at least in comparison to us. But if you do the whole E equals mc squared, that seems to be the maximum unit energy because the Planck mass happens to be a maximal limit. Okay. Of unit, because if you throw a Planck mass into a Planck volume, you're going to be creating a black hole, as far as we know. Okay. So that seems to be kind of the end of the line as far as we know it. Maybe there's some more there. I know the Wolfram Physics Project conjectures that there's kind of more stuff going online underneath it all. Is like an underlying computational aspect to it. I'm personally quite sympathetic to that. Uh, I can't necessarily say I know what it means, but I'm going to present what we know according to current physics, as far as we know, mostly from like Wikipedia and Wolfram Alpha and everything. And again, feel free to trust, verify. A lot of the stuff, as far as we know, has been known for a while. And again, as we've gotten more precision with our technological observations and everything, we'll be able to probe further and further and get some more significant digits, if you would, aka more digits after the decimal point. Why? Well, if you're trying to create something of high precision, like I don't know, a fancy cell phone, a computer, a high power race car, Or perhaps you're trying to send something into space and you want very precise calculations. Those extra significant digits help. That's the whole, when you hear something about a tolerance, like we have this engine board over to X number of microns or something like that. I might be a few magnitudes off there. I haven't paid attention to a lot of automotive engineering in a while, but that's that whole concept of if you have very high precision, your calculations for what's going to come out from it are going to have better agreement. So if you're more precise, we can do more cool stuff. That's basically the gist of it. Hey, welcome, K Show. Thank you for joining, my friend. We're just going on the maximum of temperature, and I know for those of us here in the in the northern hemisphere, it can get quite hot. Now, on a typical scale of us imperialists over here that they'll use Fahrenheit and everything. Yeah, I can get really hot, at least on the East Coast. I remember hitting 90, maybe pushing towards 100-ish degrees. That's pretty hot, especially relatively if you have humidity. So if you got more humidity in the air, what's that mean? There's basically some more water vapor around. And if you have that high temperature, guess what? It's going to kind of feel like a sauna. It's kind of like when you go to Florida after the standard afternoon shower. That seems to always happen for like 10 minutes downpour. And then immediately after, you go outside, any wrinkles in your shirt are going to kind of go away until you start gushing sweat and you look completely drenched. At least that's my general experience. There's a lot to like about Florida. In the summer, it gets really freaking steamy. But yes, trade-offs. Everything in life is kind of a balance there. Flowing through all, there is balance. Insert the gray Jedi code here. Okay, so what are we talking about? All right. So we're gonna get into something, and I realize some of this isn't gonna make necessarily sense, but we'll get to the point. Okay, so I'm gonna have to follow this convention. Maybe I'm gonna have to rename this. Let's throw in our friend temperature. So I think my AirPods decided to work either after an I don't know an Apple update or something like this. So if I'm facing the board, I still should be coming through. So we're gonna throw our next friend here. Temperature. Temperature. Boom. Okay. Then you have a line down there. I'm gonna say the base is big T because it's really hot, as opposed to little t sub p, which the Planck time is really freaking small. It's about 10 to the 32 Kelvin. I believe that's, yeah, big K because it's a name. All right, big K. There we go. All right, 10 to the 32 Kelvin. Really freaking hot. So I think like the largest temperature it's been created here on Earth, as far as we know, is at CERN's Large Hadron Collider. I hit about 1 trillion degrees. What what is that? Well, a million has six zeros. A billion has nine zeros. A trillion has 12 zeros. 10 to the 12. Freaking amazingly hot. And we seem to be able to probe into some of the inner workings of reality as far as we know. Okay, that's 10 to the 12. This is 10 to the 32. You need like an extra 20 zeros after what we've done at the Large Hadron Collider to hit the magnitude of the Planck temperature. Basically, it's estimated that if we're going to rewind back to a beginning, a hot, dense state, perhaps a Big Bang, if you would, and again, that's people can disagree about that, but if we were to rewind to a very hot, dense state, it's estimated that that would basically be the creation of reality as we know it itself may have been at the Planck temperature. Because right now, the average temperature of the universe, as far as we can see from the cosmic microwave background, is about CMB is about 2.73 Kelvin. All right. So for those of us paying attention, this is a magnitude of one. This is 10 to the 1 Kelvin. Okay. This is 10 to the 32 Kelvin. Very, very ginormous difference. Okay. So we got a few numbers here. How the heck do we come from this? All right, let's delve into a little bit of the stuff. So let's just share with the class. Boom, boom, boom. Okay, so don't mind me. We're skipping ahead. I'm going to create a new window. Okay. So using our friend Wolfram Alpha, which happens to be, again, I'm very biased here, one of the greatest sources of units within humanity that I know. Again, Professor Wolfram last time he'd said, as of now, it's got like over 10,000 different units. So here's the thing: you don't gotta be a genius. You don't gotta memorize all this stuff. You just gotta know. All right, we got some stuff. It's doing some things. How do we get to this stuff? Okay. So thing is, the Wolfram language is a natural language. You can literally just type in Planck with an N there. Planck temp or temperature. Okay. So what's defined as this. So as we know, and Rick has stressed this, the we're taking the radical, aka we're taking the square root of this following expression. What is this expression? This is the maximum speed, the speed of light, raised to the fifth power. Why? Because that's how it works. Maybe it's telling us something more. Maybe it's just a coincidence. Okay. But and then we've got the elementary unit of action. So a maximum speed to the fifth power times the elementary unit of action. This is Planck's reduced constant, aka h bar. And that's all divided by big G, the Newtonian gravitational constant. Thank you, Newton, as well as Boltzmann's constant. That's that little k squared here. Sometimes you'll see it as k sub b. That's Boltzmann's constant for helping to compute entropy. And basically, if you multiply temperature by that, you're going to get its energy equivalent. And then I believe if you divide by it into energy, you're going to get temperature. Something like that. We'll find out in a second. I always confuse those two. But as we can see, yeah, yeah. 10 to the 32. That's our base? WTF, mate. Now, that base might, when we say base, what does that actually mean? Maybe an interpretation is maybe this is our kind of base scale for our initial state as far as we can understand it, or at least as far as we can follow. I'm not going to start from that whole ontological. It's like, all right, how do we get something from nothing? I can't do it. I either need some form of configuration space, maybe an infinite dimension Hilbert space, or at least a void of randomness, waves, Roolead, whatever you want. And at some point, you're going to have a configuration that comes together. And I'm just imagining as Thad has taught me, and as Jennifer Sharp, shout out to Jen from the Church Entropy channel, that whatever that random waviness is going to come crashing in, and it's going to invert into the hypersphere of maximal volume, which is the claim of where we live. And again, a lot of people can disagree with that. That's fine. We are conjecturing. I think a lot of people get in trouble when you start going on and it's like, well, this is the case. Okay, perhaps it is. But as soon as you start stating that is, maybe somebody does have some extreme divine knowledge of what's going on. That's totally a possibility. I've run into a couple of folks occasionally where they'll be explaining something. It's like, well, it is a solution to the collapse conjecture and everything, and that's cool. And then they end with that quote unquote that they are somehow the savior reincarnated or something. Now, that might be true. That could be true, but I sit back and I'm like, okay, well, this person is Jesus. Now, Jesus, here's the thing. I still don't understand what you're saying about the collapse conjecture. That's fine because people like to argue about different things. My thing is, I don't really care who somebody is. It's like as long as you're not like harming children or doing anything horrible, like you never know where a good idea can come from. That's my general take on that. Uh, yes, yes. Well, we're talking about yes. Welcome, Poindexter. Yes, we are talking about a limit here, and again, we're going to conjecture because I'm going to do some calculations. I'm going to give some of my inferences about how I'm kind of thinking about that. And as well, hey, it's a live stream. That's why we want interaction. We want people because I don't know everything. I barely know a dang thing. I'm basically just a monkey with a magic typewriter and maybe an idea of where to look. That's all I am right here. But it's like you come to these things from the sum total of human knowledge. That's the thing. So a lot of these things that we have here, yeah, guess what? That was built on the work of Euclid. We use that stuff, and it was it still is extremely useful, and we're using it millennia later. So that's the power of mathematics. Because if you can get something in mathematics and you prove it, it's yeah, that probably ain't changing. You might conjecture, you could be wrong, but proof in mathematics is the proof, of course, of course. Alrighty. So we got a maximum temperature. So let's let's do something that we did before. Okay, so we're gonna go over here. So we're gonna do our whole thingy here. Hold on, let me go back. All right. So all right, let's take this off. All right. Let me go back one more. All right. So the whole thing here, we have our conversion factor. And again, this is kind of just it's actually kind of naive here. What are we doing? We're taking, let's duplicate this and move it over here, just so I can do this. All right. So we're using our little field thingy that we had over there. Okay. What's that field thingy? It's the field thingy, this one. All right. I'm stealing Thad's old symbol, or basically the Chinese symbol for field. And that I've been using that as the inversion box. He changed it to the little like hourglass thingy that's more over here. So I'm like, well, that's a free thing. That's a bunch of squares. What am I doing? All I'm taking is meters. So the reference of length divided by the minimum of length and squaring it. Okay, so a reference unit divided by the base unit, that all squared gives us a ginormous number. What's that ginormous number? Oh, it's this guy right here. 3.8 times 10 to the 69. Okay. All that is the inverse of the Planck area. So just to verify it's again, you can just type natural language. You don't need to know all the different numbers and everything. So Planck area is going to give us like 2.6 times 10 to the minus 70 meters squared. If we do 1 over the Planck area, we get that 3.8 times 10 to the 69. But that's in reciprocal square meters, which apparently this number, if you throw in Planck units, does kind of pop up within the Klein-Gordon equation, which I just I haven't spent the time looking at the Klein-Gordon equation. It's very important. Again, I'm not a good physicist. I think the way Casey put it is I'm basically a numerological. I think he's a physicist. I'm not necessarily even sure I agree with that because I feel like that's actually a good title, and I don't qualify. All right, but we got this number here, so all right, that looks a lot like hold on, this is our previous number here. Okay, that's the same thing. This is just the dimensionless component here. And again, maybe this doesn't make sense, but it's okay. What happens if we did something different and we did, I don't know, let's elementary charge, okay, the charge of an electron or a proton, divided by the Planck charge. Okay. Oh, the lag is real. Let's reload. There we go. Uh, oh my God, the hiccups, the hiccups. Let's. Wow, my point is literally in limbo. Well, these things happen. All right, so let's. Technology is great as long as it works. So let's go to a different thing here. So we'll go back over here to our point. If our other window decides to actually cooperate, we can go back there. All right. So right now we're over here. All right. So we're conjecturing now. This is a limit, so to speak, but that many Kelvin for what? Okay. So I'm going to write that number down, but when we say that, it's again, the Planck temperature I claim is basically just like the Planck mass. Why? Well, because you can use the Boltzmann equation to go back and forth, and if you divided it by a Planck volume, you're essentially going to have the equivalent amount of Planck mass, Planck energy, or Planck temperature within that enclosed thing, which at that point, again, you're reaching a limit because, as far as we know, that is when you create a black hole. Okay. So, minimize this because I'm bad. Yes. And as Poindexter's point out, there is also a minimum bound. I believe we got that from the ideal gas law, that they could have a lower bound, which, as far as we know, is 0 degrees Kelvin. I know it's actually a zero there. Now, the interesting thing is, once you get 0 Kelvin, okay, we can't really hit 0 Kelvin as far as we know because there always seems to be some thermodynamic stuff going on. Because if we, okay. Oh, look, our other window finally worked. Okay. So going back to our other thing is, all right. So we did elementary charge over Planck charge squared. Wait a second. This number looks pretty familiar. Look up fine structure constant. Oh, oh, the lag. The lag. Okay, we'll move you back. Long story short, that's basically the current value listed on Wolfram Alpha for alpha, the fine structure constant. Okay, so we're back over here. So let's write that down. That's a limit, but a limit for what? Based upon this squared relationship. Okay. So we'll put down. How can there be a Planck temperature? We're gonna get to that, Mr. Gregory. We'll be right there. So, all right. What was our number over there? Hold on. Cover it up. All right. 5 points. Okay. So again, the claim is we're taking big T, so the Planck temperature, and again, this is conjecture. We're just following the concept of maximal extendability. The concept of maximal extendability is there's no arbitrary boundaries, the best of my understanding. It's that if we have minimums, aka or a basis of reality following our coherent system of units. And again, the coherence of this, don't believe me, believe Maxwell, believe all the other smart people, or don't believe them. Again, maybe it's wrong, but it's just if you can go from force equals mass times acceleration, energy equals force times distance, and then the power is the energy divided by time, you got a bunch of energy on your laptop battery, and then depending on how much power you need to draw will lead to the amount of time your laptop battery is going to last for. And then usually around the end, they usually start lagging because I've done live streams before, and it's like, why am I getting so laggy? Oh, my computer it's not plugged in. It's getting ready to just power off. So yeah. Okay. So we're taking the Planck temperature, which is a base, at least according to this. And again, if there are better words for this, let me know. I could just say Planck units, but that seems more arbitrary. But I'm going to make the claim that this is the base temperature. And Mr. Grant Gregory asked the great question, how the heck could you have such a ginormous temperature as your base? Okay. So we have this, and again, this is going to seem to be messing up what I'm saying, but we'll go through. So, and again, we're taking the same thing. We're taking meters squared. Oh, I did that wrong. I've been putting it on the inside. Okay, so we need to put that on the outside. Oh God, fake science. Heck, I might be talking about fake science, and I'm even getting my own science wrong. Hold on, that's why proper notation is important. All right, so we got m, which is meters, divided by the Planck length, and then we're squaring that whole thing to get our 10 to the 69 number there, or basically that thingy there. So we just go by, and all these things we could replace with those blue boxes because that's just notation. Why you'll see like E equals mc squared, and yes, that's it. God, that is beautiful notation. I'd love to be able to find an equation like that. But you have that, but there's actually more to it. It's actually like, what is it? MC squared plus the momentum, and then another c squared, and you got to add and take in the relativistic accounts and stuff like that. So, okay. So this is approximately ginormous temperature. All right. 10 to the 101 Kelvin. All right. 10 to the 101 Kelvin. That's crazy. I mean, look at this. It's like, well, if this is a limit, what's the claim for here? We're going down and we're utilizing just a very simple, non arbitrary, we're just basically taking the reference of length, dividing it by the base of length. In this case, happens to be a minimum. We're squaring it. And then we're just multiplying all these things by the individual units to see if we can't figure out something that might be going on. And to be fair, all we're doing is basically taking that magnitude, and most of these magnitudes are going to end up coming to be the same thing, but at least we're trying to establish an ontological framework, basically how we're thinking about things, and we're trying to think about them in a coherent way, because if they're coherent, then we can move back and forth and we have logic that we can follow. Now, you can argue that there's a better way, but well, however you're trying to think about reality, you want to be coherent, right? I mean, that's ultimately what we want to do. And then we incorporate humanity, and then, yeah. Okay. 10 to the 101 Kelvin. Oh my God, what's that? Oh, look, it's 69 orders of magnitude difference. Yeah, because that's what all these things are going to come out to be. Uh, yeah, because that's the difference. Okay. So why am I showing you all this? I just literally just multiplied it by a ginormous number. Let's see. Speed of light comes, this paradox of the point where space-time might fluctuate. Okay. So this is interesting. It's Mr. Grant Gregory, but it's also Mr. Grant Gregory AI. Is the real Mr. Grant Gregory please stand up? Please stand up. Okay. Let's go back here. So why any of this? Okay. That's a ginormous number. I don't know what to think of that number, but you know what? Wolfram Alpha's got a bunch of things to say. Oh, there's also another planet I like. Uh, according to Wolfram Alpha, the acceleration needed, basically, if you were to accelerate and emit UNRWA radiation, which we believe, or many people believe is a thing, or Stephen Hawking's, the gravitational acceleration needed to achieve that temperature is 1.337. 1.337. Decimal point after the one to the 122nd power for acceleration. Well, up bigger than the Planck acceleration. Okay. I thought that was neat. Okay. So in order to figure this out, if you're going to talk about temperature and you want it to kind of make sense, go to our good friend Boltzmann. Boltzmann, or I can spell sometimes. Boltzmann constant. All right. Well, you multiply by the Boltzmann constant. Oh, look, hey, we get a number that seems kind of familiar. Now, if you've never seen any of these calculations, again, don't worry. This shouldn't mean a dang thing to you. All this is this is the equivalent energy, because Newton meter, or the joule, is our unit of energy. And again, the joule is equivalent to, literally, it's our reference of energy. So our reference is kilograms. Let's write kg. Kilograms. Oh, look, I have it right here. Basically, that whole E equals mc squared. So we've got meters squared over seconds squared equals 1 joule. Okay. Or 10 to the 7 ergs. That's a highly underrated unit, I'm going to claim. Been depreciated. That's a shame. I appreciate our depreciated friend. Okay. And gives you all this info and everything. Okay. So what is this? This is just literally, if you were to take this looked like E, energy, equals mass if you change this to c squared, you're going to get the relativistic energy. But the joule itself is literally reference mass times reference length divided by reference time, and that all squared. Oh, that's energy. Okay. Why am I doing that? Because this energy right here, we go down, oh, this relativistic math. Because remember, equals mc squared. So we want to go back, divide this whole dang thing by c squared. So we get this number here. What is this number? Well, for those of you who've been checking up on some of these things, if we do our little notation there, we get our meters over the Planck length. So we have the reference of length divided by the base of length, or a minimum of length in this case. We square that whole dang thing, we get our big number. And then if we multiply that by the Planck mass, that was a 10 to the 69 number. The Planck mass is an order 2 to 10 to the minus 8 given our system. Oh, look, we get our number in Planck masses, which is, oh, that 8 times 10 to the 61 kilograms. Oh, look, 8.3 times 10 to the 61 kilograms. It's the same number because, well, duh, because we're multiplying it by the same factor. So basically, we just pull these factors out because that's kind of just a little trick to assume that there are no arbitrary things. So we just did that. We hit enter there. We're taking the Planck temperature or maximum temperature times Boltzmann's constant is going to give us an energy divided by that c squared, bada boom, bada bing. 2.1764 times 10 to the minus 8 kilograms, aka the Planck mass, which is 2.1764 times 10 to the minus 8 kilograms. It's the same thing. We're just adding that magnitude factor that I claim is at least a logical, ontological way, an ontologically logical way. I know it's a lot of ons in there. An ontologically logical way of determining perhaps the limit of our realm. Now, again, perhaps it's infinite because that whole thing is, well, if space-time basically, if you could go down beyond the Planck scale, because a lot of folks are looking for sub-Planckian physics and stuff. If you could go beyond the Planck scale and you can continue to infinitely divide, infinitely divide, infinitely divide, and you continue to go down for infinity, well, if you did 1 over infinity, you're gonna get infinity. So that means if you can continually go down forever and ever, that universe as we know it should continue to get larger and larger forever or ever. Now, depending on what framework or ontology you subscribe to, you might think, well, if we expand enough, eventually the fabric of reality is just going to rip apart and we get one of those big rips. That sounds pretty terrifying, but to be fair, I mean, we wouldn't notice because it's kind of like hitting the history eraser button. You're just going to go kind of like poof. Without the poof, we're just going to cease to exist. Okay. So, hey, Morgan, welcome. Welcome for, thank you for joining. Let's see, it's warm is a limit of temperature for the entropy of hot and cold. Ooh, I have not heard those words before. And the question is, how do we define warm? Because all I know is, at least subjectively, humans occasionally disagree. Uh, yeah, it's, don't worry, Grant. Even the folks in the Wolfram Physics Project, if you go over to the thing, it's even Stephen Wolfram's like, okay, we have this rough calculation, and it's they're kind of doing conversions for Planck units to try to get physics, and then just map it out using hypergraphs to try to count things and account for the features of reality. Okay, so that's done. Okay, so what's the point? Okay, I showed you these things. Why? We're talking about temperature. Let's go back to temperature. Okay. So let's go back one more. Okay. Because I was just showing you things that were equivalent. Because even if we take that mass, we multiply that by c squared. Oh, look, we're getting that. Oh, hold. I'm not even showing you. It's like, oh, he's just randomly going around. All right. So basically, if we take this expression here, the Planck mass, so the estimated mass, in this case, we're converting it to energy or estimated mass energy bank of universe for mass is about 7.488 times 10 to the 78 joules. Okay. Now, I'm saying those numbers for a reason. There's a reason I'm saying those four digits and not just the magnitude, because we're gonna show you something kind of cool. All right. So again, if we went through this again, so we got our magnitude factor squared, or our magnitude factor here. We got the Planck temperature. Our multiplying by Boltzmann's constant to get the energy. Okay, so we're seeing that 7.488 times 10 to the 78 joules. All right, so that's the same as mass. So that's why we're establishing just as bases, or it's a base for these dimensions, aka the numbers that we get out. We can get out similar things. All right. It's basically the whole coherent units. We can go back and forth. Then these are essentially ones of base within our system. Okay, let's get to the payoff because we've already used half our time and we're still talking about this. Okay, so hypothetically, what would happen if we're saying that's a limit? Okay, was there something that we could try to do? Let's how do we want to do this? Okay, I think we might need to actually go here. I know, we're adding Boltzmann's temperature. Boltzmann's constant. Actually, let me do this because I think I did this before, but it didn't necessarily work. So let's okay, so we're gonna oh jeez. I'm terrible at sharing, I apologize. Okay. So if we assume that's a maximum temperature, and then we've got that energy there. Okay. So we got a maximum mass energy equivalence for temperature. So hypothetically, what would happen if we, oh, I don't know, let's divide it by something like the Planck pressure, because that also happens to be a thing. So let's actually go over here. We'll show you what it is. So the Planck pressure. I think we could also say perhaps this is the basis of our system. Why? Look how ginormous that is. That can't be a base in a system. That must be a limit. Okay, perhaps it is a limit, but which limit? Okay, so it's defined by this here. So it actually is not a square root, which is interesting. That's the speed of light, the maximum speed to the seventh power, divided by the Newtonian gravitational constant square divided by h. But don't worry about that. All you need to know is you get out a unit of pressure. These are the dimensions. It's a mass divided by a length and a time squared, or at least in the denominator, because those minuses are down below. So now, why? That doesn't seem to make sense. But if you think about it, we're taking an energy and then we're dividing it. Mass equals, oh, let me go over here. So E equals mc squared. So we get something like a Planck mass. All right. And c squared is approximately Planck length divided by Planck time. Planck, because a length divided by a time is a speed. And the minimum of length divided by the minimum of time yields the maximum of speed. We square that. So we're going to get a maximum of unit energy, the Planck energy. Okay. But now let's divide it by meters cubed because we can. So we're saying we're putting that energy within a volume. Okay. Gives you this number, but more specifically, I should actually just do the same units. So let's divide by the Planck length, aka the Planck volume, excuse me, Planck length cubed, which would be the minimum of volume as far as we know. And you get the Planck pressure, which is this ginormous number here. Okay. So let's go back and we're going to divide by the Planck pressure. Pressure. Yes, because I'm obviously part Hobbit. Hairy feet. What's this? Okay, here's where we start getting to the payoff. Is because this number right here. Don't worry, you don't need to know this number. But these digits here are interesting. These digits, exponential power, the units are interesting because we go over here to this cubic meters. Okay. So if we just take off the cubic and we were to express that magnitude in meters, oh, look, comes to be, that seems to be the Planck length right there. Why is it times meters squared? Because, so we could just do this. We just write Planck length because that's expressed in a length, and we multiply it by the reference unit squared. Okay, so we're getting that number. And again, this is just all kind of coincidence. If you do the math, this is what's going to be coming out to because of ratios. Let's take it a step further, my friends. Okay, because what we just claimed over here is if we took, let me go back to the Planck pressure for just a second, because here's the thing. I'm just going to write Planck pressure. Yeah, I've never actually had this discussion, so thank you all for bearing with me and helping me to figure this out. I know I'm horribly ignoring the chat. I'll be right there. The Planck pressure, okay. A limit of pressure, but if we divide by c squared, listen, if you see something that doesn't really make sense, very often multiply it by c squared. Divide it by c squared. It took me a lot of messing up and basically just having to learn more. What do we get? Oh, we get the Planck density or Planck mass density because all it is we just do Planck density. Take that off. I know I'm going kind of fast, but the Planck density is basically a limit of density. Or perhaps in this case, maybe we're claiming it is a base of density. We're going to get into that. All right. So it's this ginormous number here. All that is it's mass divided by length cubed, or a volume. So all it is the Planck mass divided by the Planck length cubed, or the Planck volume. So it gives us that number there. And then all we do is, if we took that mass and we multiply it by c squared, oh, look, we get the Planck pressure. Okay. So the Planck density is a maximal density of that stuff, and the Planck pressure is a maximum pressure. So basically, it's the energy equivalent to a mass density because it equals mc squared. Ah, see what I did there? Okay, I'm gonna get to the actual payoff about why this is actually interesting. I know it's taken me about 45 minutes to get there. I've been showing all these equations. Here's the thing. Feel free to. I want people to be able to do this stuff themselves because one of the things is when I started seeing Thad do this stuff, I was able to replicate very basic things, but I hadn't used this. I'm not a physics student, at least in the traditional sense of the word. But okay, let's get to the payoff now. 40, going on 44 minutes in, because 42 might explain a lot, but I claim 44 explains more. All right. So we got a cubic meter here. So since this is in units of meters, what's the length? We've got a volume. Let's do some magic. We're gonna take the whole dang thing, and we're gonna oh, I did that wrong. We're gonna raise it to the 1/3 power, aka we're taking the cubed root because if you took it to the square root, that would be 1/2 power. All right, so we're gonna take it to the 1/3 power to get out a unit length for our claim of, all right, if we were to take the maximal amount of temperature within the universe and we were to condense it all back into a very, very hot, dense state. In this case, it would literally be the Planck temperature per Planck volume. If we were to take we had a volume there, and what happens if we take the cube root of that volume, we're going to get a length. What length do we get? Is it something interesting? Okay. So, oh, I didn't even raise it to the power. Bad beams. Okay. We got this. All right. 10 to the minus 12 meters. That doesn't mean a dang thing to me. Maybe it does to you, but that's the benefit of Wolfram Alpha. It's a computational knowledge engine, so it does a lot of the hard stuff for you. Thank you, Team Wolfram. Okay, so about three times the distance between atomic nuclei and a white dwarf. All right, that's kind of cool. All right. It's about the 120th the Bohr radius. Is this something interesting? As a wavelength, oh, what's this? Huh. Seems to be just a little bit larger than the Compton wavelength of the electron. That's interesting. Okay. Huh. So the claim is that if we were to rewind to a very hot, dense state, that a lot of folks know is that the size of universe, using small u because avoiding the container problem, we took small u universe. If we were to rewind to, let's say, quote unquote, an initial state that we can try to comprehend the entire size of our realm of existence. It's about the size of an electron. That sounds coincidentally a lot like a primordial atom, if you would. I just did some calculations. That's what it happened to come out to be. Um, and again, you can feel free to disagree. This could just all be complete bunk. But as far as we know, from these five dimensions or five platonic dimensions of measure, time, space, in this case, a unit of length, charge, mass, and temperature, from all those dimensional ingredients, you can make the constants of nature, as far as we know. Now, occasionally you'll see like an angle in there for some stuff, but you realize angle doesn't have a meaning unless you're comparing differences of lengths. You need some magnitude in there to get angle. Um, but I was kind of skeptical, and then I was actually going through and doing a calculation. I'm like, oh my God, that is right. You can actually generate the constant of nature from just these five things. Five is a lot less than infinity. Now, it might be hard, but even I can count to five. All right. I apologize. That was a very circuitous route. Oh, and this whole thing is if you were to rewind back down to that, let's say, primordial atomish state, um, that's base of temperature is going to be the Planck temperature. We were just doing the energy equivalence for sake of notion, but if you do it, it would have either a mass density of the Planck mass, it would have an energy density of the Planck energy per Planck volume, and it would have a temperature per Planck volume of the Planck temperature. See, that's why these are bases, or at least why I listed them in that categorical fashion. Again, maybe there's better stuff. So let me tune back in. I apologize. I'm a terrible host. Let me read and drink some caffeine. Oh, Mr. Grant Gregory, here's the thing. Right now, even at the Large Hadron Collider, at about 10 to the 12 or about a trillion-ish degrees or so, trillion, maybe 10 trillion, could be off by a little bit there, which turns out to be a lot of it. But at that magnitude, that's the thing. Even Professor Sean Carroll, in his biggest ideas of the universe, he starts going through sizes and magnitude. I didn't necessarily know what he was talking about the first time, but after going through and listening for like however many times the algorithm keeps sending me back there, because a lot of times I'm looking up something. Oh, biggest idea. Oh, this actually kind of makes sense now. I can actually do some of the calculations. But yeah, even at like 10 trillion degrees, which is the hottest temperature that we've basically observed, at least on Earth. Um, yeah, a lot of particles as we know it, or at least protons and stuff. We smash them together. Yeah, we can. Okay, well, that was energy. Yeah, basically at the Planck temperature, you, you basically end up Here, I think Google actually had a pretty good explanation for this. I know. Oh, I didn't want to Google. So let's go here. So the Planck temperature. Blah, blah, blah. Yeah. So basically, what you do is at this temperature, the wavelength of light emitted by the thermal radiation reaches the Planck length. Okay. So if the Planck length is the minimum of length, and you're you're going to have a wavelength, um, yeah. If you can't get below that, that's why things kind of start to break down. People start looking for sub-Planckian physics and stuff. Um, Depends on its. Okay. I'm gonna put a pin in that one. I'm gonna put a pin in that one because it's not for the scope of this video. The Planck temperature, yeah, it particles really can't exist. As far as we know, if you're at the Planck temperature, I think a proton would probably just be. Maybe we began with just matter and antimatter, and we got to where we are. What I'm at least conjecturing here, you could totally do that. You could totally do that. You could take basically your standard lambda CDM cosmology and everything, and you could apply it to this. Why? Just because I'm making the claim that, well, if we want to follow a logical basis for how we might determine a maximal size of the universe, well, or yes, maximal size. I'm using the word size. I have to be careful with my language. But if we have a way to perhaps compute some limits to reality, now some of these are maxes, some of these are minimums, but at least if we were to rewind to that hot, dense state, a maximally dense state, these units seem to hold and make sense at that scale. Scale also, coincidentally, is about the size of an electron, which is interesting because it does seem to be the minimal stable elementary particle. Okay, basically, you smash some electrons together, you're basically just going to get some photons and just standard other elementary particles out. Basically, the electron seems to be the end of the line. After that, you're just getting energy and excitations within whatever the vacuum, which is technically not a true vacuum, and you could get other particles and stuff. That's why the benefit of at least like a muon collider or something is you're smashing protons together. As far as we know, protons are made up of other stuff and everything. Okay. The electron doesn't seem to be made of other stuff. Yeah. Uh, I mean, I have my own personal ideas of that. What happens if hypothetically, because I was trying to think, I'm like, all right, if we start from matter, antimatter, that makes a lot of sense. But why do we have that asymmetry? Why does there seem to be a lot less antimatter than matter as far as we know? The only difference with that is basically like its charge or technically its spin. So if you were to think if matter spins in one direction, antimatter spins in the other. Other than that, everything else is aligned. But if you have a matter particle of a particular type and an antimatter particle of a particular type, and they come together, they eliminate and they turn into pure energy, aka photons. So, and again, I'm going off on a tangent. Take what I've said before, let's truncate it, because hold on, I need to play the Wolfram thing to cover my butt. Let's media assets. So we're going to conjecture ahead here. All right, there we go.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
I love that clip so much. Okay, so wait a second. All right, so if we talk matter and antimatter, and again, this is conjecture at this point. We have matter and matter and antimatter, and they come together and they eliminate photons. Okay, so hypothetically, if we let there be light, could we potentially get to a universe that looks kind of the way it is. Okay, let's rampantly conjecture ahead at this point. Uh, Hold on, I'm going to show something. I'm updating this poster. This is going to be something I'm going to be showing at Demysticon 2025. Anastasia and Shiloh from the Demystify Side podcast are holding a scientific conference in Sembra, Portugal, in a couple of weeks, and myself and Thad are going to be attending, and we're going to be presenting a couple of posters and stuff. So, how the heck could we get from light to particles as we know it, or at least the stuff and things that seem to be going on within our realm of persistence? Okay. So let's bring this up. ECC, aka Eternal Cyclic Cosmology. What the heck is this? All right. So the claim is this thing right here, aka the complement of the hyperbolic figure eight knot. And I understand there's some cutouts there, but just imagine this thing like it looks like a ball or a sphere. So the thing is, if we zoom way, way in, let's see. All right. If you see in there, I know it's kind of pixelated, but it's like there's basically a figure eight knot there. All right. All that is a torus with a figure eight knot in it. Yeah. You could happen to create it according to William Thurston uh, by taking two ideal hyperbolic tetrahedra. Okay. So you take a tetrahedra, you take a tetrahedron, and you can glue them together in a particular way, and you can have a spherical type shape that's going to have a knot, but there's a little throat here, there, that goes in and goes through there. All right. So that's the whole point. So hypothetically, if we were to let there be light at this very hot, dense state, the size of an electron approximately, and so let's say I'm probably gonna have to update some of these things, but all right. Hypothetically, if this thing was to articulate and go through an action, basically at one point through this throat, the surface would be coming out, and then at one point it could be going in. So this was undergoing a very particular action, I claim. I don't know this, but if this was acting in some way that it was sucking up light, let's say if you would, and it's going through this very elaborate process where it's being like undergoing some figure, it's going like literally at the speed of light, and well, by definition, kind of has to. And if you have like the medium itself being sucked up and then going through, being basically turned around, not quite at a right angle, but like smoothly all the way this way and looping around all the way another way, all while undergoing a Mobius twist. According to Thad's calculation, this throat of this vortex reaches approximately the charge radius of a neutron. Okay, that's interesting. Basically, the magnitude of the Planck charge in meters. Really small. The interesting thing is Kali, shout out to Kali from Kali Fisher on YouTube. She's proposed neutron decay cosmology, which the claim is it's very simpler. Well, it's very simple in that he's basically proposing a very similar thing. She just happens to be using a trefoil knot. So basically, her claim of neutron decay cosmology is at some point you're going to hit a maximum density, and that maximum density is a neutron. And at some point, neutrons are going to pop out. And once you have a neutron, well, if it doesn't bind with anything else within about 14 and a half minutes for some reason, it decays into a proton, an electron, and an antineutrino. Wait a second. Those seem to be a lot of the building blocks that we need for the stuff of our reality. Oh, very interesting. Uh, Ultimately, I'm not going to conjecture that in the actual poster because, I mean, we're already, the conference is about alternative cosmologies. Basically, a lot of people believe in the standard Big Bang Lambda CDM. Okay. Now, the James Webb is providing very interesting information, which kind of like the Hubble at the time, it's like we learn more about what was going on. As we learn more about what's going on, our models, we adapt them, and perhaps there's other ways to explain what's going on. The whole point of this poster is to explain for a physical explanation for dark energy. So basically, the whole claim is for those of us that were fortunate enough to do this experiment in middle school, you take a couple of soda bottles. All right. You screw them together. You have some water in there. You give it a good shake. Gonna create like a little vortex, and it's gonna be vortexing out the other side. All right. So the claim is this toroidal hyperbolic figure eight knots complement, aka it's I'm claiming it's the one, aka it's an oscillatory network engine, aka the one. I know, yes. But the claim is at some point, wherever we are right now, and again, you can argue I have some calculations that it depends on dark energy if it's a constant or it's related to the total mass bank of a universe. They do calculations different ways, but that's going to make a big difference. I don't know. So ultimately, the claim is we have this thing spinning around, and if this thing was spinning from an early time, well, that would probably add in some form of a rotation gradient. So if there's a little bit of angular momentum, might that explain why, I don't know, certain observations, there seems to be a preferred direction of galactic rotation? Well, that's a very interesting thing. Now, and again, that's conjecture, but that's going to be part of the paper. But the ultimate claim is, all right, so if you have this thing doing some type of a vortex effect, and it's sucking things in. They're being compressed going through this highly, almost spinning around this way, undergoing a Mobius twist, and going down to about the charge radius of an electron. Could they be getting constructed extremely densely, and then as they're coming out the other side, basically be expanding and be what we may observe as a hot, dense state akin to the Big Bang. Because if we had this cyclic rotation, well, number one, it's a lot of people don't like this because, as far as we know, if we rewind general relativity and all that stuff, uh, two backwards, we tend to get to about like about 14-ish billion years. Okay, now is it possible? And to be fair, I think the answer is possible. Yes, we don't know, but I could totally rewind and we could go back here. Perhaps, maybe, I don't know, there was a cluster or a black hole, maybe a supermassive, hypermassive black hole that is getting ingested. And at least according to the Schwarzschild solutions to general relativity, it's, well, black holes we didn't think were a thing. And we seem to get white holes out of them, apparently. So, what happens when you invert a black hole? Sounds like you might see something kind of like a white hole, which would kind of be, oh, I don't know, a lot of extremely hot, dense material coming out and then forming what we may know as our observable universe. Okay. I realize I've gone all the way off the wagon at this point. Uh, but at least at that point, if you're going to have some vortex like structure, or just if you've ever put, like, I don't know, any of those Mio or flavor enhancers in the water and you see stuff dispersing, or if you've ever literally boiled a pot of water, you get convection, hot, cold. What happens if we're really hot here? We're going out, we're expanding, and perhaps there's some rotation going on here. Stuff's going to go around, and eventually it's all going to loop around. And the cycle would lead to some form of persistence, or at least I claim would be a physical mechanism for dark energy. Now, in order to try to fully substantiate this, aside from just a couple of pictures of some soda bottles and a little picture that I did in Microsoft or Apple Pages or something like that, it's like, yeah, you're going to need to have some form of a rigorously constructed field theory to actually postulate this. Okay. Now, what that exact field theory is, I don't know. Now, that's the benefit of string theory. For all the things that people gripe about string theory, it's mathematically rigorous, which is probably why a lot of people like going to it. Now, if we could connect something like that to our world, that might be very encouraging. And there might be some hints within this that through potentially the Leech lattice, which apparently if you get 3 copies of E8, uh, at that point you can explain, I think, the standard model of particle physics and stuff. But you're going to need to have an explanation for that. Okay, I realize I digressed for God, far too long. Okay. Well, that's about all we've been going through. Let me catch up. God, I missed so much stuff. All right, let's go back. Who uses orgs these days? Well, I claim the org might be making a revival at some point. Let's see. Ba-ba-ba. Hot and cold. Well, to be fair, I actually learned from somebody within the engineering world that I used to think that heat heat rose and stuff like that, but technically that's not true. It's more like just cold stuff. Just I used to think that cold went down, but it's more like just hot stuff has more energy. So if you're in gravitation or something like that, it's gonna be moving around, probably hopping more. Hey, what's going on, Jax? Good to see you, my friend. Yeah, we're just going through some stuff and some things, conjecturing rapidly. Yes, welcome, Maria. Good to see you. Good to see you. Yes. Oh, Maria is going to be popping on, so we could feel free. Oh, can I actually? I have no idea how to send people over there. Is there stuff here? Okay. I don't know. I apologize. But if you like some art stuff, feel free to check over Maria at Unlocking the Lore. A limit applies infinity does not exist. Okay. So it depends on how you would conceptualize infinity. Okay. There's only one infinity on here that I claim, and this is more of an ontological preference, is if you were to have something that were to persist, it might be finite in size, maybe a ginormous radius, maybe like 10 to the 34 meters in radius. But if that structure has the ability to persist, especially if it does hit its limit, maybe it's going to have a big crunch back down. I don't know. It's to be fair, I don't think that's necessarily ruled out, but at least for me, it's a very beautiful thing that if you had something like this and it was designed, oh God, I need to be careful with my language. If it took a form that could persist, perhaps time as we know it may actually continue on in perpetuity. I think that's a very beautiful thing. How would you explain that? Well, technically, if you take the hyperbolic figure eight, no, it does project at infinities at some point, but maybe you could say that's, I don't know, time and then frequency. I don't know. Rampant speculation there. Uh, oh, well, you were timed on your first time. Well, Jax, you can be kind of spicy. So then again, if you're having an Audrey like Venus flytrap that's eating things, listen, I understand. Different folks always listen. Somebody's channel, they can do what they want, blah, blah, blah. It's totally fine. All right. And oh, geez. So if we were an avatar with an experiment living in a simulation. Okay, so the crazy thing is, at one point, we had just finished recording like a talk or something. It was like a year or so ago. And at one point, Echelon's talking about it's like, oh yes, we would like to ultimately end up engineering some technology. Why? Because well, if we have five dimensions of measure, we already have three like 3D printers. If you incorporate those other two dimensions and you get them at a particular area where we could potentially reach, we might actually be able to replicate like almost anything. Imagine it's like the greatest tomato in the world. You can just have the data, it's upload, you could have fresh tomato, and that would be at a true post scarcity thing. But in order to do that, you're going to have an enormous amount of power. So basically, we're going to need at least fusion style technology, superconductive energy transfer, and then basically be able to design, which seems actually feasible within maybe about 50 years. Again, maybe that's just some well thought thinking on my part, but yeah, it's I guess the old noggin a jog. All right, let's see. Da, da, da. Do I think that all the models are wrong? No, I think a lot of these models are telling us very useful things. Uh, well, the interesting thing they're pointing us is if an error was injected into the machine code of the universe and observed it corrected itself. Is it error? Because I thought about this myself. Is it error correction or error prevention? That was something I learned from Rick. So again, Swift recovery is my friend. Uh, Morgan is saying that the inside out black hole is an Earth. To be That's interesting. I haven't heard that before. But to be fair, okay, I got to show one last thing, just because this is crazy. Or at least this is a very weird thing. All right, let's go back over here. All right. So hypothetically, do one over the, let's do kilograms because kilograms is our reference one. If we do it squared, that'll give us a dimension. Okay, let's just do this first. One over the mass of Earth. Okay, it gives you these numbers, but they're in reciprocal kilograms. We want to do our little continuing hack. We just multiply it by kilograms squared. This kilograms would net out a dimensionless number, and then kilograms squared will give us a unit with dimensions. Okay, is this that? Huh, wait a second. The inverse of Earth is approximately the mass of the Z boson. Don't that just beat all? Again, that's just an interesting coincidence, but Morgan brought it up, and I'm like, I did kind of play around with these calculators, so I just had to share that. But now I'm far too late. But hey, that's all we got for right now. Thank you all for joining, and those who may be joining temporally in the future. Again, this is conjecture. Could all be bunk, but then again, it's a different way of looking at things, and at least it's a particular ontology or way of attempting to frame things in a logical, coherent sense. So, other than that, take care of yourselves and is open for a better tomorrow. Peace out.